All right, good morning, everyone. My name is Yang Kim from Ewha Women's University. Today, I'll present the paper titled SketchFeature, High-Quality Per-Flow Feature Extractor Towards Security-Aware Data Plane. This is just overflow of this presentation. With the rise of AI enhanced in-network defense, the ability to process high-quality packet features efficiently has become even more critical for network security. Incomplete or low-resolution feature extraction can lead to misclassification or blind spots, making networks vulnerable to attacks. To enable fast attack mitigation, real-time feature extraction is necessary. However, feature extraction in the data plane remains a challenging problem due to hardware limitations. In network measurement, features can be categorized based on their dimensionalities. First-order features are per-packet features, such as protocol type and TTL. Second-order features are per-flow statistical features, including flow size, mean, and variance. Third-order features capture per-flow distribution, such as inter-packet delay distribution or packet size distribution. It is well established that higher-order features enhance attack detection capabilities. However, extracting these features in data plane is challenging due to high computational overhead. A symptom detector is a selective feature extraction mechanism in the data plane, and it escalates only a subset of flows to the control plane for attack detection. So instead of performing full per-flow feature extraction, it filters flows based on predefined symptoms. Among such symptom detectors, FlowLens and NetWarden are two notable approaches. FlowLens uses a hash table to quantize per-flow distribution ranges and stores only the top K bins. However, this approach is vulnerable to evasion, as attackers can slightly shift the packet size pattern, avoiding detection. As a result, FlowLens cannot generalize well to unseen attack variants. NetWarden utilizes a sketch-based approach to store per-flow distributions, but at a relatively low resolution. Due to this, it is vulnerable to control plane floating attacks, where adversaries can overrun the system by triggering excessive flow escalations. Also, its low-resolution quantization leads to misclassification, as small variations in feature values may fall into the same bin. So the limitations of FlowLens and NetWarden stem from the constraints of the data plane. The data plane must guarantee line rate packet processing, which restricts computation to simple arithmetic operations. And memory resources are extremely limited, preventing the storage of detailed per-flow distribution features. So to ensure robust feature extraction in the data plane, a better approach is required. Instead of selectively extracting features from a small subset of flows, feature extraction should cover all flows. And instead of storing only top K bins, the full feature distribution range must be extracted. And feature extraction should achieve high resolution while minimizing memory and computational overhead to sustain line rate processing. Now, we introduce our proposed scheme, SketchFeature, which ensures half feature measurement. So half stands for high resolution, all flow, and full range. It eliminates top K bias and detects a wider range of attacks with better granularity and accuracy. When designing SketchFeature, we addressed key challenges by introducing new strategies called sketch virtualization and membership test. Furthermore, we theoretically proved the error bounds of SketchFeature's encoding and decoding process and experimentally validated its accuracy and efficiency. Finally, we demonstrated the superiority of SketchFeature by comparing it with existing schemes across various security use cases and successfully deploying it in a Tofino commercial switch. Now, I'll explain the design of SketchFeature. First, SketchFeature reduces the complexity of per-flow distribution by quantizing continuous feature values into discrete bins. So after quantization, the system records how many packets fall into each bin per flow. So this bin-wise representation shown in the figure on the right side is called a distribution vector. This quantization process is necessary to cope with the memory constraints of ASIC-based switches, and it is also used in FlowLens and NetWarden. So this distribution vector is stored using a data structure consisting of a sketch and a Bloom filter, as shown in the figure. By encoding and decoding in this data structure, the distribution vectors for all flows can be retrieved. Now I'll show you the encoding process of SketchFeature. With quantization, it determines which quantized bin the feature values falls into. And this bin number is used as an input of a hash function for Bloom filter and sketch. And to record the presence of this feature, the corresponding Bloom filter bit is set to 1. And the sketch counter is increased by 1, indicating that a feature has been added. In the decoding process, the flow ID and the bin number is given. Then it first checks the Bloom filter to verify whether the feature exists in a given bin. If the feature is present, it retrieves its value from the sketch. Since SketchFeature is based on a count min sketch, it obtains the minimum value across all sketch layers to minimize errors. After the decoding of all bins, we can get the full distribution of the flow. And there is a hidden optimization in this design, which is sketch virtualization. Existing methods use sketch partitioning, where each discrete bin is assigned to a separate, physically isolated sketch. However, SketchFeature shares a single sketch across all quantized bins, distinguishing them using hash functions. So the upper side of the figure shows the baseline, which is sketch partitioning approach. If a specific bin contains a large amount of data, the corresponding sketch can become highly congested, reducing accuracy. On the other hand, sketch virtualization inherently provides a form of load balancing due to the uniform characteristics of the hash function. This enables efficient memory utilization regardless of the feature distribution. So to validate this approach, we analyzed memory usage patterns under skewed feature distribution as shown in the upper figure. So in the figure on the bottom left, sketch partitioning shows heavily populated bins indicated in red, suffering from extreme congestion, which makes it difficult to obtain accurate results. In contrast, sketch virtualization distributes data more evenly, leading to higher accuracy and efficient memory usage. The second key innovation in SketchFeature is the membership test, which resolves the phantom decoding issue. And phantom decoding occurs when a query retrieves a non-existent bin value due to sketch collisions. So in other words, even if a bin was never actually encoded, the sketch might return a non-zero value, leading to false positives. So as shown in the upper figure, QL1 has an entry of 0 and has never encoded a value to the sketch. But however, when queried, it returns 2 due to hash collisions, as illustrated in the bottom part of the figure. SketchFeature applies a membership test to solve this issue before querying the sketch. So it ensures that the queried bin actually exists before retrieving its value. This approach significantly reduces the false positive rate, improving overall accuracy. So the first figure highlights that in sketch virtualization, first, false positive errors caused by phantom decoding which is indicated in yellow, exist true positive errors indicated in gray. But after applying the membership test, which is the bottom figure, the false positives are effectively reduced, enhancing feature extraction accuracy. The left figure presents the CDF graph of the WMRE metric, evaluating per flow distribution quality across 3 different schemes. So WMRE closer to 0 means higher accuracy. The results indicate that applying sketch virtualization enhances feature measurement accuracy. Moreover, incorporating the membership test to form SketchFeature further improves it. The right figure compares the traffic distribution quality of baseline and SketchFeature against the actual distribution represented in yellow. Since the y-axis is on a logarithmic scale, the baseline demonstrates error exceeding a factor of 10 in the worst case. In contrast, SketchFeature closely aligns with the actual distribution, exhibiting significantly improved accuracy. So by combining sketch virtualization and the membership test, SketchFeature achieves high accuracy, efficiency, and scalability, making it applicable to a wide range of security applications. So we evaluated feature quality of IPD and packet size distributions under various datasets and with different memory size using matrix WMRE. As shown in the figure, across all memory size, SketchFeature significantly outperformed the baseline. And also same for the various workloads, SketchFeature outperforms baseline. Lastly, we tested attack detection using extracted feature distribution across multiple security use cases, including covert channel, DDoS, and botnet detection. The results show that SketchFeature produced feature distributions closest to the perfect measurement, proving its superior detection performance in AUC, accuracy, F1 score, false positive rate, and false negative rate. In summary, SketchFeature successfully enhanced sketch capacity and resolves technical challenges in sketch-based measurement, and is deployable in commercial switches, and is both theoretically and experimentally validated, confirming its accuracy, and is well suited for security applications, offering superior feature extraction for network defense. Thank you for listening.
So for the attacks you had, can you go back 2 slides, I think?
Okay. Oh, it's not working.
Okay, no worries. So you showed attacks for the, how do you detect the attacks? Like, is it you use the features as a measure in the classifier and be able to
Yes,
differentiate
exactly.
between attack? Okay, and then what's the benign like? Can you just give some information about how you set up the experiment? Like how much, what did you use in terms of the attack? What type of attack? Let's focus on the DDoS, for example.
Oh, focus on the DDoS. So we use CIC DDoS dataset, and benign dataset was CADA dataset, and we we evaluated like 4 different schemes: NetBeacon, like NetWarden, FlowLens, and ours. So 4 different schemes, and also perfect measurement. So we extract the feature using these like 4 different feature extractor, and then use this like extracted feature as an input of like CNN. Like we trained model using that feature that we extracted, and like use it as a attack detection. And perfect measurement means that we extracted feature like the actual number, like the actual distribution of feature. So we compare the attack detection accuracy, like F1 score, and just the accuracy, like false positive rates and false negative rates. Yeah.
Thank you. Any other questions? Let's thank our speaker.